This is a video lecture on the complex Fourier series. Suppose we have a signal, f of t, and we desire to decompose it into some set of basis functions. And we'll decompose it, in general, in a set of functions called phi sub I of t, where phi sub i's, where I is the index, are all orthogonal to each other. In other words, if we took the integral over the period over which we desired to represent f of t, we took one of our basis functions, phi sub I, and we multiplied it by another one of our basis functions, took the derivative of that, then if I was not equal to j, so these are two different basis functions, then the integral would be 0. Then we say they're orthogonal. Otherwise, if j is equal to I, so we're really taking the integral of the square of phi sub I, then we get some non-zero value. For the complex Fourier series, we use the set of basis functions e to the j n omega naught t. Where we would write omega naught could also be defined as 2 pi over t, the period over which we are trying to approximate f of t by this weighted sum of basis functions. So we'll describe this approximate function as f hat of t, where it is the sum, a weighted sum of all of the basis functions. So we have a weighting factor. We'll call it f sub n, and we're going to sum from minus infinity to infinity. And we'll take the product of that weighting function, or weighting term, times our basis function, n e to the j n omega naught t. Okay, so this would be something like f sub minus 2 e to the minus j2 omega naught t plus f sub minus 1 e to the minus 1 omega naught t plus f sub 0 e to the 0, which is going to be 1, plus f sub 1 e to the j omega naught t plus f sub 2 e to the j 2 omega naught t plus dot dot dot. And we can determine these coefficients, these weighting terms, according to the complex Fourier series integral. So f sub n is equal to 1 over the period over which we're going to compute we're going to do the fit. So this could be from t naught to t naught plus the period. And it would be f sub t times e to the minus j n omega naught t dt, where omega naught is 2 pi over t. This integral comes about through a calculation of the mean square error between our f sub hat and the actual function f. And when we minimize the mean square error, we come up with an expression for f sub n, which is this one here, specifically for the complex Fourier series. So these two statements here, this and this right here, comprise our Fourier series, complex Fourier series definition. All right, let's consider some examples of signals before we go too far into using these definitions. It's important to have some familiarity with f's of n. Okay, just to kind of think of a signal in terms of the weightings of its basis functions, or its complex exponential functions. So let's consider f of t that's equal to, let's say, 3 cosine t, 3 cosine omega naught t. By Euler's formula, and what I mean by Euler's formula, recall that e to the j theta is equal to cosine theta plus j sine theta. Okay, and we can use that and express cosine in terms of these complex exponentials, which would be 3 times e to the j omega naught t plus e to the minus j omega naught t, the whole thing over 2. So we have 3 halves e to the j omega naught t plus e to the minus j, plus 3 halves e to the minus j omega naught t. So what we have is, for f of t, we would have f of n is equal to, well, it's going to be, well, we'd write it this way. F of 1 is equal to 3 halves. F of minus 1 is equal to 3 halves. And all other f's of n's are equal to 0. We can plot that where vertically we have f of n and horizontally we have n, or n omega naught. And what we have is 2 lines, really just 2 points, at 3 halves, and it will be occurring at plus omega naught and minus omega naught. And that we call the spectrum of 3 cosine omega naught t. Now what if we have a function f of t equal to 3 cosine omega naught t plus 2? Well, there we'll have the 3 halves e to the j omega naught t plus 3 halves e to the minus j omega naught t plus, we can say, 2 e to the j 0 t. So now our spectrum looks like this. We would still have the 3 halves at omega naught and minus omega naught, but now we would have, okay, this is 3 halves. We would have another spectral line right at 0, right here. Okay. So if you see a function f of n that has a non-zero value at the origin, the frequency origin, then you know that it has a DC offset. So in time, what would this look like? It would be an offset of 2, and then it'll have an amplitude of 1.5. Okay, this would be f of t. Let's look at yet another example. What if f of t was equal to 3 sine omega naught t? Then we would have 3 times e to the j omega naught t minus e to the minus j omega naught t over 2j. This right here is sine omega naught t. That comes from the Euler formula. So we have 3 over 2j, which if you multiply, by j over j, then this becomes, the jj becomes minus 1. So we have minus 3 halves j. E to the j omega naught t minus 3 halves, actually it's going to be a minus 3 halves j e to the minus j omega naught t. So the spectrum there, I better move that up, n omega naught, it will be at, let's see, at omega naught it's going to be minus 3 halves j, minus 3 halves j, and at the, I did that, yeah, and then at the minus omega naught, it'll be plus 3 halves j. Okay, now let's consider yet another example. What if we had f of t is equal to 3 cosine omega naught t plus, let's say, plus the 3 sine omega naught t. Okay. So we'll have 3 halves. I can write it this way. We'll have, so we'll have 3 halves e to the j omega naught t plus 3 halves e to the j omega naught t plus 3 halves j e to the j omega naught t, and then minus 3 halves j e to the minus j omega naught t. Well, I think I got the sign wrong on that. Yeah. Yeah, like that. Okay, so let's combine our terms. We have 3 halves minus, well, we actually have 3 halves times 1 minus j times e to the j omega naught t, and then we would have 3 halves times, oh, I got a minus sign missing there. I forgot the minus there. And then we'd have 3 halves times 1 plus j times e to the minus j omega naught t. Okay. Now we can write this here. This is a complex number, right? This is 3 halves, and then 1 minus 1, if we draw that on the unit, on the complex plane, we would have 1, and minus j would be down here. So this right here is 1 minus j. And we could write it as magnitude of square root of 2, right? Square root of 1 squared plus 1 squared, the real squared plus the imaginary squared, times an angle of minus 45 degrees, or minus pi over 4. So let's go ahead and write that here. This would be square root of 2 with an angle of minus pi over 4, which is minus 45 degrees, times e to the j omega t, plus, and here we'll have 3 halves times root 2, which incidentally is 3 over root 2 alternatively, and then we have angle of plus pi over 4, or 45 degrees, e to the minus j omega naught t. Okay, so now we would say f of minus 1 is equal to 3 halves root of 2 angle of 45 degrees. F of plus 1 is equal to 3 halves root of 2 angle of minus pi over 4, and all other f of n's are 0. So how would we plot that? We could do it this way. We could plot n omega naught. We could do the real part of f of n, and then we could plot the imaginary part of f of n, that would be fine. But we can also, and preferably, plot the magnitude of f of n and the angle or argument of f of n. Okay, so let's fill this out. So for the real part, we would have, if we go back up to what we had up here and here, so at plus omega, we have a real part of 1, and we have an imaginary part of minus 1. Change the color here. For the n minus 1 case, we have a real part of 1, and we have an imaginary part of 1. Okay? So you could draw it that way, represent it that way. The preferable way, though, is to use the frequency domain, or the magnitude and phase. So here we have the magnitude for both plus n minus omega naught is going to be 3/2 root of 2. Okay, and we would say then that, let's say the angle is going to be pi over 4. So pi over 4, I'll just say 90 at 45 degrees, or pi over 4 at minus omega naught, and it will be minus pi over 4 minus pi over 4, or minus 45 degrees at plus omega naught. Okay, so let's draw a conclusion from this. So referring to the magnitude and the angle plots of our coefficients f of n, we notice that the magnitude of f of n is an even function. Now maybe it's not very clear here because we've only plotted, just the n equal to plus 1 and minus 1, but this will be true in general. And notice that the angle of f of n is an odd function. So for instance, if you have a magnitude plot that looks like this, so let me draw some kind of a shape here. We would have all the discrete harmonics fall on that line. It turns out that if you look at the corresponding negative values of n, they will have the same values. Okay, so i.e. no new info is given by plotting the magnitude of f of n for negative values of n. Okay, so we can just look at positive values, knowing that it's reflected over for the negative values of n equal as well. All right, but you typically won't see a magnitude plot showing the magnitude spectrum of a signal looking at both positive and negative frequencies because they're symmetric. And in fact, the same thing can be said of the phase, because if it turns out that the phase, let's say it's something that looks like this, right? So we'd have discrete lines here, discrete points, I should say. Okay, so ditto for angle of f of n, because if we know that it's an odd function, and it turns out that for n equal to 1, we have an angle of pi over 3, then for a frequency of minus omega naught, okay, right here, we're going to have an angle of minus pi over 3 because it's an odd function. We can show this by looking at the integral that computes these coefficients. F of n is 1 over t, the integral over a period of f of t e to the minus j n omega naught t dt. Now if we replace n with minus n, so it's kind of just a variable substitution, then we'd have f of minus n is equal to 1 over t integral of f of t e to the plus j n omega naught t. Alright, so if you look at that, the magnitude, okay, note the magnitude of e to the j n omega naught t. That's terrible. What is the magnitude of that? It's always 1, right? Because we're on the unit circle. This is the imaginary and real. So regardless of whether you have a minus sign in front of your exponent, it's not going to change the fact that that has a magnitude of 1. So when you take the magnitude of the integral of f of t times e to the j n omega naught t, changing n to minus n is not going to change the magnitude. So that's going to give you, that results in the evenness of the magnitude function, and then because we see that it just flips the sign of the exponent, and that's the only place that the argument of f of n comes from, we can conclude that the argument function, argument of f of n, is an odd function. Now this assumes that f of t is real valued, okay, which is always the case, you know, in real physical systems. F of t is going to be real valued, not complex. So let's recap this idea of the frequency response or frequency representation of a time domain signal f of t. For this case of f of t equal to 3 times cosine omega naught t plus sine omega naught t, otherwise written as 3 root 2 cosine omega naught t plus pi over 4, okay, you can equivalently represent that signal in the frequency domain by the f of n, the magnitude and the angle plot of f of n. And so this Fourier analysis allows us to do a transformation. So we can do a Fourier, we can do a transformation between time and frequency, or frequency and time. And we'll find that there are some uses for going from the time domain to the frequency domain, and when it's easier sometimes to use the frequency domain representation of a signal to be able to do some processing on that signal that we might want to do. So think again in terms of systems. You might have some input u of t, you might have an impulse response of a system h of t, and you can think of what is their frequency domain representation. And we'll find that things like doing a convolution in the time domain in order to find the response of a system due to an input u of t can actually be turned into a multiplication in the frequency domain. Now we won't see that yet because we're still looking at Fourier series right now, but we will expand this to Fourier transform, and that's where we'll see a lot of this come to fruition. So for a given signal, you could be given two equivalent one of two or both equivalent representations. You could be told some signal f of t is defined by f of t equals ... or you could be told that some time domain function f of t is defined by f of n is equal to ... And in both those cases, the information that would be provided is equivalent. It's just in a different domain, time domain versus frequency domain.